Hello everyone. As part of learning Spark, let us see some more concepts related to Spark. We will talk about various types of variables available in Spark. Generally, whatever variables we are working in Spark, we have a category called as shared variables. These shared variables are used by multiple functions, and you can make sure that multiple methods can use them in parallel. Then they are used in parallel operations and allow for efficient data access across the nodes. How many types of shared variables are there? We have broadcast variable and accumulator. There are basically two categories of shared variables. So let us look at what do we mean by broadcast variables and what are accumulators, where they are needed. And whenever you are talking about shared variables, obviously the concept of consistency comes into picture. Spark will take care of consistency and parallel sharing of these variables across the nodes. So let us talk about broadcast variable. Broadcast variable, whenever we are trying to work with broadcast variable, one copy of the variable will be kept in the cache memory so that you need not transfer the variable every time it is needed by the programs. So suppose there is a variable which is very frequently accessed, make sure that variable is kept in the cache memory instead of transferring it across the network. What are you going to save out of this? The moment you are not transferring data over the network, you are trying to save the bandwidth and the transmission time also. So this reduces the shuffling of data across the nodes, and broadcast variables are created from a variable by calling the method. What is the method? Spark context dot broadcast. Whichever variable you want to put it into broadcasting, that variable should be passed on. I will show you this with an example. And broadcast variable wraps it around the variable v, and its value can be accessed by calling the value method, broadcast.value or the variable.value. And see the example code for broadcasting a variable. If you just see this example, VAL, that is variable, we are trying to declare a variable. The name of the variable is lookup, and what did we specify? It's a broadcast, that is the name we are specifying, broadcast. And what is the type we are trying to do? We are using a map where key is of data type integer, value is of data type string, and what did I specify? Is equal to sc dot broadcast. SC stands for Spark context. So we are trying to use the Spark context dot broadcast method to which you are submitting the variable. What are the values you are submitting? You are going for a map wherein key is given with integer and value is given with string. So the moment you define, this variable will be stored into the cache memory, which can be used across various nodes in parallel. Now, how do I take the value? Val result is equal to sc dot parallelize. We know whenever something is to be used in multiple locations in parallel, we need to use the parallelize method. And what did we specify? Map lookup dot value. How do we access the value of a broadcast variable? Using the dot value method. So we are trying to access it using lookup is the broadcast variable name. We are trying to access it using lookup dot value. So this is asserting that the value is so and so. What is the value? If I take the key values 2, 1, 3, what are the values we are going to get? It is a set consisting of the values A, E, I. Because you are trying to work with a set, the order of the values doesn't matter, whether you are taking from the specific index values or not. That matters. So the major concentration here is how are you declaring a variable as a broadcast variable and how do we access its value. Now, what do you mean by broadcast variable? Generally, whenever you go for something called as broadcasting, from the source, it is reaching to multiple destinations. Can the destinations respond back? That facility will not be there in broadcasting. For example, television program broadcasting. radio broadcasting. In such cases, it is from the radio station or TV station towards the individual televisions of various customers or clients. Can they respond sitting in their home and can they respond in that particular program thing? No. So, broadcasting is generally one way. Similarly, broadcast variables are also one way. What do I mean by that? From the source, I can try to store its value in multiple locations so that they can try to use it in parallel. The updated value will not be transmitted back to the source location. That is one way of the broadcasting variables. Just try to understand this one. As the name suggests, broadcast variables are sent one way from the driver to task, and there is no way to update a broadcast variable and have the update propagate back to the driver. So, backward propagation of the updates is not possible. From the source or from the driver, the value can be sent to multiple locations. That's it. If I want to have the updates also propagated back to the driver, then I need to have the second type of shared variable, accumulator. So, remember the two categories of shared variables. First one is the broadcast variable, which is one way wherein the driver can send the value to multiple locations, but you cannot get the updates back to the driver. If I want to have the updates to be propagated back to the driver, we need to have something called as accumulator. What is an accumulator? It is also a shared variable which tasks can add to, like counters in MapReduce. Generally, whenever you are trying to work with accumulator, it does with the addition operation, addition logic. So, it is like a counter whose value can be incremented, right? So, an accumulator is a shared variable which the tasks can only add to, like a counter in MapReduce. After a job is completed, please mind this one, the accumulator's final value can be retrieved from the driver program. So, who is the driver? The one who is trying to control how the value is to be passed between various locations or various nodes. So, when the driver program is circulating the value of the accumulator, whichever node is trying to update the value, its updated value can be accessed back from the driver program. Here there is an example which counts number of elements in an RDD of integers using an accumulator. Just go through this program. Val count is an accumulator of integers. How did we define? SC dot accumulator of 0. I am sending the accumulator's initial value as 0. Then what did I specify? Value result is equal to SC dot parallelize array of 1, 2, 3. We are passing on the SC dot parallelize array of 1, 2, 3 dot. What is the map method doing? Whichever I value it receives, it is trying to increment the count value for every I value. And what is the reduce function doing? It is trying to take both x and y, whatever values it is receiving, it is trying to sum them up. It is trying to find out x plus y. And what are we trying to ascertain here? The count value is equal to 3 and the final result is equal to 6. What is count value? What is result? Count, initially you started with who is the count? Accumulator. What was the initial value for accumulator? 0. So, you are trying to keep on incrementing whenever you are sending an I value. What is the array number? What are the number of values in the array we are sending? In my example, I am sending 3. So, how many possible values I will take? I will take 3 values. So, what happens to the counter? You start from 0 plus 1 plus 1 plus 1. So, you have sent 3 values in the array, the counter will be incremented thrice, and what will be the final value of the count? 3. Then whenever you are trying to call the reduce method, you are sending values x and y, you are trying to sum them up x plus y. So, what will be the sum of values when you are sending through the array. First time you might have sent 1 and 2. What it will do? It will add them up 1 and 2, the value will be 3 and the result will be kept into the first component, that is x. Next time what values do you send? What is the current value of x, that is 3, plus what is the next value of y you are sending? 3 there. So what you will do? 3 plus 3, 6. And the ascertains will be true and the final value will be retrieved from the driver program. So whenever you are trying to work with accumulator, it will try to send back the result to the driver program. That is the essence of accumulators. Broadcast variables, as it is to be understood, it is a one-way variable. When the result of the spark job has been computed, the value of the accumulator is accessed by calling value method on the accumulator variable. Now, anatomy of a spark job running. Whenever a spark job is running, how do we talk about the various steps involved in this spark job? When we are running a spark job at the highest level, there are two independent entities. I will just show you the diagram. So when we are running a spark job at the highest level, there are two independent entities running. First one is the driver, the second one is the executor. Who is a driver? What are the steps involved in the driver? And who is an executor? What are the steps involved in that? Let us just go through them. So whenever we are trying to run a spark job at the highest level, there are two independent entities. The first one is the driver, which hosts the application and it also holds the spark context, and it schedules tasks for a job. Whatever job you have submitted, the jobs will be having multiple tasks. So all those things will be taken care by the driver. So the driver is having the application, it acts as the host of the application, it holds the spark context and it also schedules the tasks of the job. The executors, which are exclusive to the application and they run through the duration of the application and execute the application tasks. So what are the executors? They are the exact statements which are trying to complete the tasks which are generated by the driver. So usually a driver runs as a client which is not managed by the cluster manager, and the executors run on machines in the cluster. What do we mean by this? Generally the driver, you can think of the driver is getting executed on the client machine where the job is initiated. Once the job is initiated, the tasks have been generated, the tasks will be running on the distributed network. So the actual tasks are managed by the cluster, whereas the driver is working on a local machine where the client is initiating the task. Spark job, first if you see the steps, spark job is submitted automatically when an action is performed on an RDD. So we know resilient distributed data sets, whenever a particular action is taking place, we try to call it as an RDD. So spark job is submitted automatically when an action is performed on an RDD. Internally, this causes a run job method to be executed by the spark context, which passes the call to the scheduler which runs as part of a driver. Just go through this one. Whenever the spark program is submitted, it automatically initiates an action on the RDD and it calls the run job method on the spark context. This spark context tries to divide the activities and passes on to the DAG scheduler, directed acyclic graph scheduler. So the scheduler is made up of two parts. One is a DAG scheduler which tries to break down the job into a DAG of stages, and a task scheduler that is responsible for submitting the tasks from each stage to the cluster. What is this DAG scheduler? What it is trying to do? It is trying to divide the job into a DAG of stages. Every stage will again have a task scheduler which is trying to execute the tasks which are generated by every stage of the system, every stage of the application. So this DAG scheduler tries to divide the job into stages, and every stage has certain tasks to be performed which are taken care by the task scheduler. Now, to understand how a job is broken down into stages, we need to take care of the type of tasks which will be executed at every stage of a Spark system. Two types: shuffle map tasks and result tasks. What are shuffle map tasks? These names have come depending on the type of task and what type of output is getting generated by the task. Shuffle map tasks. These tasks are like map side work of a MapReduce program, and each shuffle map task runs a computation on the RDD partition, and based on the partition function, whatever partition we are trying to work, it tries to write its output onto a new set of partitions, and all these individual results can be taken in order to submit it to the final stage, right? This is somewhat like you are trying to divide the task and execute individual tasks, just like we do in divide and conquer. We are trying to divide a big task into individual tasks, trying to conquer individual tasks and put the results in one location. This is similar to that, not exactly. Then coming to result tasks, the result tasks run the final stage which returns results to the user program. What it is trying to do, it is trying to run a computation on the RDD and sends the result back to the driver. What is the driver doing? Whatever results it is getting from individual RDD computations, it tries to accumulate them and tries to give the result for every partition. And simplest Spark job that does not need a shuffle, and therefore it has a just single stage composed of result tasks. This is like a map only job in MapReduce. What do you mean by this? Sometimes you don't need to divide your task into multiple jobs and you don't have any partition to work. Everything can be accomplished directly. I can show the result. In such cases, it is similar to zero reduce task of MapReduce. More complex jobs involve grouping operations and require one or more shuffle stages. So as the complexity of the problem increases, we try to have multiple map methods, just like MapReduce. I am trying to take analogy of MapReduce. Say for example, you are trying to take data from a single table. One map method might be enough for us. You are trying to take data from two tables like a join operation. You might need two map methods, one for each of the tables. Likewise, as the complexity is increasing, you are trying to have the shuffle map tasks. If there is no such shuffling required, we directly go for the result task. Consider the example. We are trying to calculate a histogram of word counts for the text files which are stored in the input path, and we are taking one word per line. We are assuming the file has in each line only a single word is there. So you are trying to take the text file for which the input path has been specified. The words have been converted into lowercase, and for every occurrence you are showing the value as 1. What are we trying to do? We are trying to reduce by the key value. Wherever the key is matching, you are trying to find out sum of the values, and then you are trying to do, if at all any swapping is required, we are doing for sorting and count by the key value. Spark's DAG scheduler turns this job into two stages, since reduce by key operation forces a shuffle stage. Whenever you are trying to work with reducer, also remember in MapReduce also we have something called as sort and shuffle phase. So the same kind of shuffle stage will be required. Resulting DAG will be like this. What are we trying to do? Stage 1, shuffle map tasks. We are reading a text string from the file and trying to divide it into words and count the occurrence of every word. Then if the key value is matching, you are trying to reduce it. Similarly, stage 2, what is the result task doing? Reduce by the key value and you are trying to map the integer with the string, then trying to find out the count value. For every word, what is the count? So, if an RDD has been persisted from a previous job in the same application, then DAG scheduler will save the work and not create stages for recomputing it. What is the meaning of this one? Already I have executed some previous job which is having some RDDs which can be applied to the current job. It will not try to build it again from the scratch. It will try to use the ones which are already existing for some other application. DAG scheduler is responsible for splitting a stage into tasks for submission to the task scheduler. So, in our example, what are the number of stages we have? You are trying to have map tasks, shuffle map tasks and result tasks. So, what it is doing in our example, in the first stage, one shuffle map task is run for each partition of the input file, and the level of parallelism for a reduce by key operation can be passed on as the second parameter. And each task is given by a placement preference by the DAG scheduler. What do I mean by placement preference? Should I execute in this node? Should I execute in the other node? Where I want to place this task? It will be depending on various parameters like network distance, how many hops are needed, how much time it is going to take, whether the particular node in an active state or not, is it busy or free, various parameters. So, based on that, it will try to go for a placement preference. A task that processes a partition of an input RDD stored on HDFS, for example, will have a placement preference for the data node hosting the partitions block, like local locality of reference within the same rack, off the rack. The same principles will also work here. Then, once the DAG scheduler has constructed complete DAG of stages, it submits each stage's set of tasks to this task scheduler. The task scheduler will try to execute all the things. The child stages are only submitted once their parents have completed successfully. So, unless the parent stages are not completing, the child stages are not submitted. Task scheduling. Whenever you are trying to schedule the tasks, the scheduler is sent a set of tasks and it uses a list of executors which are running the application and constructs a mapping of task to the executor. Then the task scheduler again assigns tasks to executors which have free cores. It will not look for an executor even though it is running my application. If it is already busy, it will not try to select the same executor. Whichever executor is having free cores, that particular executor will be selected. And it continues to assign more tasks as executors finish running tasks until the task is complete. Then each task is allocated by one core by default, although we can change spark dot, task dot, CPUs. Default is one core per task. If you want, you can change number of cores based on this property. For a given executor, the scheduler will first assign process local tasks, then node local tasks. The locality keeps on increasing. So, process local tasks, node local tasks, rack local tasks before assigning non-local tasks. And sometimes we might get a speculative task also to an executor. Assigned tasks are launched through a scheduler backend which sends remote launch task manage to the executor backend to tell the executor to run the task. So, we know all these communication is happening through RPCs. Whenever the tasks have been assigned to the executor nodes from the scheduler executor, the task executor will get a message stating launch the execution of the task has been allocated. Then the executor node will finish the execution of the task and the results are sent back to the task scheduler. From there they go to the job scheduler. This is how Spark will try to execute the jobs, and it also works with various types of variables in order to process this task. Thank you.